First speaker is Felten, and he's going to talk on the top of the global logarithmic deformations.
Thanks for the introduction. This is the second part of my talk. Yesterday we learned about logarithmic deformation functor and how it can be used to show the existence of complex analytic smoothings. Today we will analyze this deformation functor. Start with analyzing complex deformation. So Y is a complex manifold. And when we have a complex manifold, we have a holomorphic derived complex. And we also have the holomorphic polyvector Px. And I'm putting them in negative degrees, so P is negative. These structures do have a number of operations. For example, we have edge product, omega I1, y, omega I2, y, omega I1 plus I2, y. The polyvector groups also have a vector product by their very definition, P1, y, P2, y, theta 1 plus P2, y. Then we have the Felten bracket. It goes from theta P1, y times theta P2, y to theta P1 plus P2 plus 1, y. And my convention is to use the negative of the usual one. It's not so important right now. And we also have the Lie derivative. Goes from theta py times omega I y to omega I plus p plus 1 y. And there are even more operations. So we have a large number of operations in the structure that essentially come from the definition. So when we have these structures, in particular, since we have these two, this thing is a Gerstenhaber algebra. And when I take everything together, then I call the pair theta ballet y, omega ballet y a Gerstenhaber calculus. I call it calculus because it's essential differential calculus that we can do in Gerstenhaber calculus. When we have the structure, now let us look at the Dolbeau resolution. This resolution is differential or analytic in nature, but it also has a very algebraic aspect because it preserves all these operations. So we can now use this is not all it's 0, to now define a yi j as omega I y tensor a 0 j y. This is just the whole resolution of the homomorphic differential forms, and we can define g pq y as theta py tensor y a 0 q y. So this is now a two-dimensional array of objects. So it's bi-graded, and there's a differential in one direction. Okay, so on the omega side there's also a differential in the second direction, but generally there's a differential only in one direction. So I call this thing a differential bi-graded Gerstenhaber calculus. Because there's only one differential. And remember, the other the round differential is already part of the Gerstenhaber calculus itself. Now we look at deformation theory through the lens of Gerstenhaber calculi. So when we have A in art, then we get SAN, which is a logarithmic space equal to SA, which is the spectrum of A. And we can look at deformations over this. In particular, there is a globally trivial deformation. It's given by A tensor C omega y. Now this thing has a resolution just by A tensor C A 0 valid y delta, which comes with one differential del bar, and since it is a resolution, we can also recover A tensor COY as the kernel of del bar from A tensor C A 0 0 y to A tensor C A 0 1 y. Now we can also resolve to the relative holomorphic differential forms of our deformation y A tensor y over SAN. They are equal to A tensor C Ty, and they're also resolved in this way. So they're resolved by A tensor C G minus 1 valid del bar. This G. So when we now have an element phi in gamma y m A, the maximal ideal of A tensor C G minus 1 1 y, then we can put it into the Felten-Eichenholz bracket or into the E derivative, and this defines a new differential operator. So del bar phi is equal to del bar plus phi, or is equal to del bar plus the E derivative, depending on whether it operates on A or G. This is a new differential operator. it goes from a tensor GPQ to a tensor GPQ plus 1 respective a tensor AIJ to a tensor AIJ plus 1. So this is a modification or twist of the differential. And this thing is not always a differential. So when you compute it square, del phi square, then it's actually equal to, maybe just do this one, del phi plus 1/2 phi, or equivalently put this expression into the first argument of the derivative. So this is possibly non-zero. But if it is equal to 0, so if del bar phi plus 1/2 phi is equal to 0, then del bar phi is a differential. And in this case, we can define O a the other way, maybe O y of a phi as the kernel of del bar phi from, let's say, a tensor a00y to a tensor a01y. This is a sheaf of rings. And since phi was actually an a, it means when we put a y, when we have C tensor a o y, a phi is actually equal to oy, and it's also flat over a. So this defines a flat deformation. So we have y oy here, and here is S0, and here's SA, and here's y oy a phi. This is a Cartesian diagram. Flat deformation. Now the situation is the following. Okay, first, y a phi is a flat deformation. Second, every flat deformation is of this form. And third, oy a phi 1 is isomorphic to oy a phi 2 as a deformation, so as a sheaf of rings that restrict to the same thing here and alinear, even only if phi 1, phi 2 are H equivalent. And this means by definition that there exists a theta in gamma x, no, not x0, gamma, y, gamma y, m a tensor c g minus 1 0 y such that phi 2 is equal to phi 1 plus the sum of n equals 0 to infinity of theta n plus 1 faculty theta phi 1 minus del bar phi 1. So the exact formula doesn't really matter right now. So this is the short Nychenhuis bracket, and this is the n-fold iterative application of taking the bracket with theta. And so these are isomorphic given only if we can find some theta here, which relates phi 2 and phi 1 in this way.
Is the first implication equivalence?
What?
Is the first implication on the right order equivalence? Can you go back if it's differential, then it's solves it? Right at the top of the right order, the very top. You conclude it's a differential. Can you go back the other way if it's differential, then it solves it?
Sorry.
If you take an element phi and you find out that del bar phi is differential, does it imply that it solves the Markov equation?
Yes.
Okay, so it's an equivalence.
Yes, and the reason is because of the operation of phi bracket on A00 is faithful. So if you have a theta, if you have a phi that operates, that maps everything to 0, then it is 0.
So it follows from item 3, you say?
No. No, you have to prove it separate.
Okay.
And point of the fact is that solutions of the yes, I didn't yet tell this. So this is called the Mora-Cartan equation. And solutions of the Mora-Cartan equation up to gauge equivalence are the same thing as flat deformations. We can define Ks y valid as gamma y g minus 1 valid y, and we call the Kodaira-Spencer algebra, DG algebra. And if we have any sub L valid bracket del bar, which need not be the Dalbot differential, any DGV algebra, then we define our MC, L valid, and A. So A is an R here, as the set of phi in L1. In MA tensor C, L1 such that del bar phi plus 1/2 phi is equal to 0. It's called the Mora-Cartan functor. And def L valid A is defined as MC L valid A mod H equivalence. This is called the deformation functor of L. And what we have seen is that flat deformation functor Y is isomorphic to the deformation functor of the Kodaira-Spencer DG algebra. So in order to study flat deformations of smooth complex manifold, it is sufficient to study the Kodaira-Spencer DG algebra. The next thing I want to do is to show you the proof of the classical Bogomolov-Dientolorov theorem. slowly. The Bogomolov-Tian-Todorov theorem. So we say that a functor d art to Z is unobstructed. If and only if for all surjections A prime A in art, it follows that also d A prime to A, the A is surject. The theorem, this is called the Bogomolov-Tian-Todorov theorem. Although there's no single article in the tree, but the tree subjective contribution to it. If Y is a compact scalar CY manifold, then def of Y is unobstructed. So what's the proof? So being Calabi-Yau means D is the dimension, is isomorphic to OY, and this induces an isomorphism of theta py with omega p plus dy. Remember that p is negative, and this induces an isomorphism between gy bullet and del bar as a bigraded monodifferential thing with a bullet y del bar. But we have a second differential here, and we can use the isomorphism to pull it back. So we obtain a differential operator delta from g p q y to g p plus 1 q y. So we get a diagram that looks like this: G00 y mapping to G01 y mapping to G02 y, and here's G minus 1 0 y and G minus 1 1 y and G minus 1 2 y, and here we get the new operator. And here in this line we have the Cordero-Spencer DGD algebra when we take global sections. So we have this thing. Now we can define K bullet as the kernel of del from G minus 1 bullet y to G0 bullet y, and it lives here: K0, K1, K2, and it maps here. And now the del bar lemma implies that G minus 1 bullet y is quasi-isomorphic to K bullet. The global sections are quasi-isomorphic by the del bar lemma. And similarly, you can define H bullet as the delta homology in degree minus 1 of G. I define HQ of G bullet QY. So you get them here: H0, H1, H2. And again, by the del bar lemma, we get gamma of k ballet is quasi-isomorphic to gamma of h ballet. And now you can actually show that these are quasi-isomorphic. So these two things also have the structure of DGE algebra, and the quasi-isomorphism are quasi-isomorphisms of DGE algebras. So what we get is that Ks valid y is quasi-isomorphic to gamma h valid S DGE algebras. But now you can show that that the bracket is 0 on gamma h valid. And now since they are quasi-isomorphic, also the deformation functors are isomorphic because the morphism of if a morphism of DGE algebras is a quasi-isomorphism, then the induced morphism of deformation functors is an isomorphism. So we get that the deformation functor of y is isomorphic to the deformation functor of gamma of h valid. And if so this thing is called an abelian DGE algebra. And abelian DGE algebras have unobstructed deformation functor. So this implies that def y is unobstructed. Crucial ingredients in this proof are this isomorphism, which allows us to get another differential on the polyvector fields, and the del bar lemma. So now we transition from smooth manifolds to normal crossing spaces. And we start with the locally trivial deformations. So maybe V is a d-semistable, although this is not essential at this point, normal crossing scheme. And then we have the locally trivial deformation functor from R to Z. Now if A is an art, then you can get a trivial CT algebra structure when moving t to 0, so by going over the factorization here. So this induces an embedding of art into art CT. And it's actually the case that def LT of V is equal to the normal crossing deformation functor of V restricted to art along this embedding. Because when you have this factorization, then the normal crossing local model is locally trivial local model. So they're the same. Yeah, so these split deformations of smoothings, they are locally trivial, and that's the reason why this the fact that I've erased that the DGE algebra controls the deformation functor works. So what we get in the normal crossing case is that we find a DGE algebra which controls locally trivial deformations. So now I say the thing is a scheme and not a complex space. So we take OY mapping to TV vowels OY del bar this thing is called the Tom-Whitney resolution. So this thing can be constructed from the scheme structure depending on an open cover. It's similar to the Shesh resolution, quite a bit more complicated. And the point is, the Darboux resolution had a property that all the structures could be extended from the thing that we resolved to the resolution. This is not true on the nodes for the Shesh complex. So we would need some homotopy burden of all the structures, which is very complicated with many structures. So instead, we put the homotopy theory into the resolution, get a Tom-Whitney resolution, and then all the operations extend on the nodes to the resolution. That's why we have to talk about Tom-Whitney resolution and not just Shesh resolution here. So we use this thing, and then we can define Ks valid less gamma v. Did I say? Yeah, their proper is not. Yeah, okay, proper is not necessary. Good. Of was the thing TV valid of the sheaf of classical derivations.
But there's also a choice going into this, right? What? The bar resolution did not have a choice.
Tom-Whitney
There's a choice.
the Darboux resolution doesn't have choice. Tom-Whitney resolution depends on the choice of an finite
Yeah,
cover.
exactly.
And okay, all my normal crossing streams are separated. So you kind of use the. I'm always assuming these things separated, and then I take a fine cover, and the sections will be a fine.
So it's not just one, the minute you choose one.
Yes.
Yeah.
But it's functorial. So once this thing is chosen, the thing is functorial for sheaves of complex vector spaces. So we don't need the OX module structure constructed. OV in this case. Yes. So the same argument works from the fact from over there. So we get that the locally trivial deformation factor of B is isomorphic to the deformation factor of the Kodara-Spencer G. But this thing is difficult to study because, okay, we can define polar vector fields and we have a DRAM complex, but it's not so well behaved for singular schemes. So what we actually want to have is an argument like this one. So we have to make it smooth. And how do we do this? By passing to log structures. So that's why I assume d-semistable, because now I can make it log smooth. My convention was to write log structures. So I set x0 equal to e as schemes, and then I turn x0 into a log scheme m0 to s0 n0, and it's possible because v is d-semistable. And then I can also look at the logarithmic deformation factor, x0 over s0 restricted to r, and the underlying deformation of log smooth deformation.
You make a statement, so you say because these semi-stable that not this is log smooth.
Because V is d-semistable, it is possible to choose a log structure on V such that we obtain a log smooth morphism to this log point. So when we restrict to these special Artinian rings with a trivial CT algebra structure, then this maps into the locally trivial deformation functor. They are not the same because the log smooth deformations, although they are also locally trivial, have different infinitesimal automorphisms. So it's not this. So we do not get. There are locally trivial deformations which are not coming from log smooth deformations, but because we are deforming in a non-d-semistable direction, and the map is also not injective because this M0 was not unique, and we can deform in the direction of choosing a different M0. And this is not seen on the underlying space. But you can just study this thing instead of this thing because it's easier to study. And again, we get, so now the log derivations. Theta, maybe -1 because I put them in negative degrees, are locally free. And we can we can nicely form the log-Yoram complex and the log polyvector fields, and also get the Gerstenauer calculus. And we can resolve it by the Tom-Whitney resolution, and then we get again a differential by the Gerstenauer calculus. And now, okay, one thing that I wanted to say is with the log derivations, we also have the LD x0 s0 restricted to art is isomorphic to the deformation functor of the global sections of the Tom-Whitney resolution of theta -1.
The same is true for the other deformation functor, right? But you can also write such an isomorphism for the other one. Use the Tom-Whitney one for the classical.
Yes, right.
And the structure maps all the stuff. Yes.
So our first approximation of the logarithmic Bogomolov-Tian-Todorov theorem is a result in an article that I have with Andrea Petacchi, H, and it's the following: if f x0 m0 to s0 n0 is a proper log smooth log Calabi-Yau, which means that the log canonical bundle is trivial. So we have log form, say the top is 0 power, and this log canonical bundle, they must be trivial. If this is the case, then g x0 of Tom-Whitney of theta -1 x0 s0 is quasi-isomorphic to an abelian DT algebra. And in particular, LD x0 s0 restricted to art is unobstructed. So this is a variant of the proof of Diacono and Manetti, who had an algebraic proof of the classical Bogomolov-Tian-Todorov theorem. But this doesn't imply smoothing, because now we have just unobstructedness in the locally trivial direction, but we would act to lift from order to order by unobstructedness in the direction of the non-trivial T algebra structure. So this doesn't help us with smoothing.
I remember that in some cases this is obstructed. Which of the assumptions you need to get rid of? You found some examples of unobstructed.
That's the next chapter in my talk.
I love.
So from art to art CT. So now definition T from art CT to set is unobstructed given only if the same thing holds for all A prime to A surjective. It holds that also D of A prime to DA is surjective. But this time for surjections in this category. So we want to show that this thing is that this functor is unobstructed without restriction. So assume, okay, so one thing that we should have if the previous proof works is that this deformation functor is controlled by a DGE algebra. So let's assume that the thing is controlled by a DGE algebra. Okay, assume exists DGE algebra L bullet, this time over CT instead over C. So every Li here is a CT module, flat and complete, and otherwise more or less the same definition, such that LD x0 S0 is isomorphic to the deformation functor associated here. So in particular, phi equals 0 is a solution of the Moragatan equation del bar phi plus 1/2 phi phi is equal to 0 for all A. And in particular, we already have a deformation to any order in a trivial way. The first means that probably there is no DGE algebra controlling the thing, at least not from the previous argument, because the argument didn't use the Calabi-Yau condition. And the other thing is, in particular, this implies that LD x0 S0 is never equal to the empty set, which is not true. So theorem by Persson and Pinkham is the following. So there exists a d-semistable simple normal crossing scheme VPP, two smooth components which in two actually intersect, so it's not smooth, such that the flat deformation functor of VPP is equal to the locally trivial deformation functor of VPP. So every flat deformation of this thing is locally trivial. And in particular, since normal crossing deformation, so this implies that normal crossing deformations of VPP over the non-trivial CT algebra CT multitude square is equal to the empty set. But now this thing was d-semistable, so we can turn it into a log smooth morphism. But if there would be now a DGD algebra controlling the thing, then this thing would be non-empty. So there would be something in LD here, which would map to something here, and this thing would be not empty. So the corollary is, in general, there does not exist a DGD algebra controlling LD X0 S0. I won't be able to finish everything that I've planned.
But how much time do you need?
I'm now 60% to the material.
You have 75%.
So let's evaluate when you do 1 hour, maybe.
Okay. Yeah, the last page is optional. I set the thought of omitting the next chapter, but yeah. So the characteristic Gauss-Hauer calculus. So in this chapter we assume that F0, X0, M0 to S0, N0 is log smooth and separated, and or alternatively we can assume that this map is a generic logarithmic family that comes with locally rigid divisorial deformations. But we can just stick to log smoothness for understanding the argument. So then we have omega I, the log differential forms. They're mapping to that on Whitney resolution. And I already told you this before. And we have theta p log derivations mapping to that on Whitney resolution. Full vector based on one account of blackboard. Okay, and this is a differential by created Gauss-Hauer calculus. But this is not the only thing of that. So we have
Sorry, just to interrupt quickly, I'm a bit behind. Why are there no coded deformations over CTT squared empty?
the normal crossing deformations.
No, sorry, normal crossing, no coded. Why is this empty?
Because every normal crossing deformation over this ring with this d-algebra structure is not locally true. But the theorem says that every flat deformation is locally true. So this is the flat deformation factor, not the flat deformation factor is equal to the locally trivial deformation factor. So every deformation has local trivial.
So normal crossing deformations were
Never locally trivial as soon as the normal crossing space is not smooth. And as soon as the d-algebra structure is not trivial in the base.
Does it mean that that space doesn't have a smoothing? The space doesn't have a smoothing? Yes. Yeah. Not even the first order.
Yes. I mean, the article is it has appeared soon after Friedman proved that d-semistability is a necessary criterion, and the point of the article was to show that d-semistability is not a sufficient criterion for smoothability, or for semi-stable smoothability. W0 and X0 open, or maybe are open. Let's just introduce a risky case. You say we have FA, WA to MA, SA, NA, a log smooth deformation, or a tensorial deformation. Then we can do the same thing. We also get omega I, WA, SA mapping to the Tom Whitney. So why does this work? Because also the deformed things are sheaves of C-vector spaces. So if any map of sheaves of C-vector spaces, between them single factorial. So omega IW SA and var, the same thing for the polyvector fields is again a differential by graded Gaussian-Haber calculus. Now comes the surprising thing. So this differential by graded Gaussian-Haber calculus, of course, depends on the Gaussian deformation. Position and so they discovered the main argument that's needed to smooth the thing. So this is the geometry of the Marokatan equation in general Calabi-Yau varieties. And the statement is all okay. So the statement as I give it is my statement, but they had the idea not to prove it, or they observed that it's true. For this thing, there exists a unique bigraded Gaussian-Haber calculus, not differential bigraded, just a bigraded Gaussian-Haber calculus, no differential. PV bullet X0A dr bullet X0A such that for all log smooth deformations FA WA SA on an open subset, there exists an isomorphism of PV bullet X0A dr bullet X0A restricted to W is isomorphic to TV bullet theta bullet WASA TV bullet omega bullet WASA as bigraded Gaussian-Haber calculi. So the differential biquadratic Garsten-Haber calculus depends on the deformation. The biquadratic Garsten-Haber calculus, upon forgetting the differential, does not depend on the deformation. And they are all compatible. So when you have two deformations, you restrict them, you get a match there, and it's compatible with this thing. The isomorphism is not unique, so this thing has non-trivial infinitesimal automorphism that we can always twist with it. Okay, so since log smooth deformations exist locally, and the same is also true for the cursorial deformations. So at least locally there is some such thing. So maybe we have some, maybe with an index alpha is a local log smooth deformation, and maybe we cover the thing with different d alpha 0. So there will be locally defined differentials del bar alpha, and when we choose some isomorphism to this thing, then this gives rise to, say, PQ x0a to restricted to b0 alpha to PQ plus 1 x0a b0 alpha. They are of course not they do not need to become the same in overlaps. But if you have a phi alpha in PV minus 1 x0a, then you get a new differential del bar alpha plus phi alpha, or alternatively plus L phi alpha. A new operator which may not square to 0. So we call this thing, so we have del bar alpha plus phi alpha square, possibly not equal to 0. And so we call it a pre-differential. And conversely, a pre-differential is some operator that is locally of this form for the given del alpha. And this is a well-defined condition, because when we have two different local log smooth deformations or two different isomorphisms here, they will always stitch out by such an element. So there's a well-defined notion of a pre-differential on this thing. And the lemma is a global pre-differential exists. It's of course not unique, because you can just add some global section of this thing. But it exists in a compatible way for all A points. So now, okay, this is first, global pre-differential del bar. The second thing that exists in L in LA in gamma x0 PV minus 1 or PV 0 times the maximal ideal, such that we have del square is equal to this thing with respective, I did 2 here, not 1. And this thing is called the curvature. So PV bullet ER bullet is curved ersten aber Calculus. In particular, we have gamma x0 of PV, let's look at some A, minus 1 valid. This thing is a curved Lie algebra. You now can look at all A's at once and take a limit, and then you will get, when you do it, so you will get a curved Lie algebra over the form of power series string and one variable here. And when you have a curved Lie algebra, then you can again explicitly compute this equation, and the new Morra-Cartan equation becomes del bar phi plus 1/2 phi plus the curvature is equal to 0. So the curvature, so this means phi equals 0 is no longer a solution, and there may be no solution, possibly explaining why there are d-semistable normal crossing spaces that have no non-trivial and non-locally non-trivial whatever deformations. And you can have again a gauge action, and you can form gauge equivalence as in curved Lie algebra, and then you have theorem that LD x0 s0 is isomorphic to the deformation functor of this curved Lie algebra. Maybe we call it, okay, this is Lx0a, L valid x0 over ct is the limit. So it's not controlled by a DG algebra, but the logarithmic deformation functor is controlled by a curved Lie algebra. So the next thing that we have to do is to analyze this curved Lie algebra.
L
The
unique?
hour is full?
Is L unique?
No. No, it already depended on the choice of the open cover in the Tom Whitney solution. It then depends on the choice of PV, and it depends on the choice of the pre-differential. But I mean, the dependence is controlled. You know how you can choose different pre-differentials. You know how whether the relations between possible choices here, and you can also relate the choices of different open covers. So they should be homotopy equivalent, but then we have to think first about what it means to be homotopy equivalent for curved Lie algebras. So actually, Fanyang and Ma proved that they're homotopy equivalent for not via quasi-isomorphisms, but via explicit, like a family of curved algebras and then a deformed. Yeah, so I can go on and explain how to analyze this functor, or I can stop. I can just tell you the main theorem.
I think we'll follow them here.
Good. Okay, so something happens, and then the corollary is logarithmic model of the Tn theorem, Tn theorem, and it says m0 x0 to s0. Sorry, not. Let's do it. F0 x0 m0 to S0 N0 zero is log smooth or mildly log singular in the appropriate sense, and proper and log Calabi-Yau, then LP x0 S0 is unobstructed. In the sense that I have defined before. Now the application, coming back to the introduction, also without proof. So V is a normal crossing scheme, and then V is stratified. So we said C0 be V and C1 be singular locus of V, and Ci plus 1 V is the singular locus of Civ, as we had yesterday. And then we said Siv is equal to Civ without Ci plus 1 V. This thing is smooth, and we can decompose it into its connected components, and this gives us stratification. In the theorem, myself and that variant thereof, V is a proper normal crossing scheme, and Calabi-Yau in the sense that the dualizing sheaf has a normal to LP, and all strata in C1 V are quasi-projective, and T1B, which is equal to X1 omega 1B or V. So this was the sheaf that occurred as the target of all my propagation blocks and structures at the end of the lecture yesterday. This thing is globally generated. Then we admit a complex analytic smoothing. So globally generated is the point of this theorem. If V is d-semistable, the result is also stronger than non-result, but not too much stronger. So the real new thing about the theorem is that it's sufficient to assume this is globally generated. And then we use Bertini on the quasi-projective strata to construct the well-behaved log singular locus and log smooth structure outside of it, turning it into a generically log smooth family, which, due to the control or the flexibility that we have in the choice of the generically log smooth structure, admits well-behaved devisorial deformations. And then we can check all the conditions that I haven't told you to conclude from the Calabi-Yau calculus the unobstructedness. And yeah, which you can do in this case for very specific local models of devisorial deformations that are more general than the one local model that we saw yesterday. And then the unobstructedness of the devisorial deformation functor follows. And devisorial deformations, then we have a formal devisorial deformation as a form of smoothing, and then from arcing approximation and drawing by V, and then everything is smoothing. Is there something that I wanted to say? Yeah, one more remark. when you look into our article, it says that C1b is projective. This condition is sufficient. When you want to allow omega v globally generated instead of isomorphic OV, then you also have to assume that the strata in S0 are projective, or assume that a good global sanction of omega is. Good. Thanks for your attention.
Thank you very much. So, any questions?